So for instance, let's say that you were asked to figure out what the square root of 12 is. So if you just think through it logically, you know that 3 cannot be the answer because 3 squared, 3 times 3 is 9. And that's obviously not the same as 12. And you know the answer can't be 4 because 4 times 4 is 16, and that's too big. So the square root of 9 is 3, and the square root of 16 is 4. So what we're asked to find, though, is not either of those. It's kind of in the middle, square root of 12, or close to the middle, square root of 12. So the answer to this thing has got to be somewhere between 3 and 4, because 3 squared is 9 and 4 squared is 16, and we're trying to find the square root of something between 9 and 16. And so it's going to be somewhere between 3 and 4. So it's good in the beginning to predict ahead of time roughly what you think the answer will be, so that when we get the answer, you can give it a sanity check. Now, if you recall, how did we teach you to do things like square root of 36? Now, you know the answer is 6 because 6 times 6 is 36, but I also told you, hey, go ahead and try to make a factor tree, right? And in this case, you could just write down 6 times 6 is equal to 36, and you're looking for pairs of numbers, and so the answer to this guy would be 6. But I also told you, hey, you could break this down further, and the reason I'm going here is because we're going to use the same technique here. You can write 6 as 2 times 3, and you can write this 6 as 2 times 3. And you're still looking for pairs of numbers in the bottom of the tree, and so you could say, well, here is a pair of numbers, the pair of 3s, and then I'll just circle the 2s right here. There's a pair of 2s. So the pair of 2s comes out as a single 2, and the pair of 3s comes out as a single 3, and 2 times 3 is 6. And you know the answer is 6, because 6 times 6 is 36, and of course, we already know that we could have just stopped right here and circled the 6s. I'm reminding you how we learned how to solve these problems before, because we're going to use the same thing. Let's do a factor tree for this and just see what it actually shows us. Let's take a look at the square root of 12. I guess I'll just go right under here, square root of 12. Now come up with anything you want. You could do 2 times 6. You could do 3 times 4. Let's do 3 times 4. It doesn't actually matter. You get the same number either way. Now 3 is already a prime number, so you can't break that down any further, but 4 can be broken down as 2 times 2. Now notice the difference between this factor tree and this one. We've broken this one down to prime numbers at the bottom. We broke this one down to prime numbers at the bottom. But in this case, we could find pairs, and once we found all the pairs, it was everything in the bottom. But in this case, we can see a pair of 2s, but there is a 3 here in the bottom of this factor tree, but there is no partner to go with the 3. This is why this answer is not a perfect whole number, because when we get to the bottom of the factor tree, when we identify all the pairs, we still have stuff left over. And that's why this one is, the answer is going to be what we call irrational. Remember, in the last lesson, we talked about an irrational number is a decimal that goes on and on and on forever with no pattern at all. And when that happens, it means we cannot write the answer as a fraction, because those decimals go on forever and there is no pattern to them. Any radical that works out to not be a perfect whole number like that is going to basically be an irrational number that goes on and on forever like that. So we have a pair of 2s, and we do what we always do. I guess I'll write it down here. I'll say square root of 12 is, the pair comes out as usual. The 2 comes out, for the pair of 2s, it only comes out once. But then you have to multiply by what? What is left over is a 3. But that 3 remains under the radical, and it's multiplied. The 2 comes out as a single, and it's multiplied by the 3 that's left over, but the radical has to be around it. Why? Because we were unable to find a partner for this. So this 3, like all of these numbers, live under the radical. The 12 is under the radical, so the 3 times the 4, the pair of 2s, they're all under this radical. But when we identify a pair, remember, we're looking for square root. We're looking for numbers that multiply times themselves to give us what we're looking for. So when we find a pair of 2s, we're only pulling out once, and it comes out of the radical. But the stuff that's left behind is still under that radical. It doesn't go away. It's still under there, so that's why we have to write it as remaining under the radical. Over here, the 2 comes out of the radical because we found a pair. The 3 comes out of the radical because we found a pair. There was nothing left, so there was no radical left. But here, the 2 comes out of the radical, but the 3 remains under the radical. So the answer to this thing is 2 times the square root of 3. This is actually what I want you to circle for your answer. And you might say, that is a weird looking answer. And you're just going to have to get used to seeing radicals in your answer. So what does it actually mean? Okay, remember what the big picture is. When we find a square root, we want to find some number so that when we multiply it by itself, we get back the original number. Now, if you go to a calculator, which we try to avoid using calculators, but we want to use it sometimes to check ourselves. And so I'm going to prove this to you. If you go into a calculator and you put 12 into the calculator and take the square root of 12, it's going to give you an answer that's going to be something like 3.46. Now, the reason I have the squiggly lines here is because this means approximately equal to. All right, because remember, it's a decimal. When you really do the calculation in a calculator, it's going to be 3.46 and then infinite decimals that do not repeat in any pattern. And that's because these radicals are irrational. They go on and on forever with no pattern. So 3.46. Now, if you take 2 and multiply it by the square root of 3, then if you put square root of 3 in a calculator, you're going to find out that that comes out to 1.73. Now, it's not really 1.73. It's 1.73 in an infinite number of decimals. I'm rounding everything to 2 decimal points here. And the square root of 3, when you put it in a calculator, gives you this. When you multiply it by 2, you get approximately 3.46. Now, the answer is probably going to be a little different in the last decimal position because I'm truncating these radicals. These radicals, anytime you see square root of 3 or square root of 12 or square root of 2 or square root of 5, when they don't come out to a single whole number, those radicals are an infinite, I mean literally infinite. Try to imagine what infinity is. It means the numbers never end. Even after the universe ends, those numbers still keep going. So these numbers are, it's really not 1.73 for this. It's not really 3.46 for this. It is an approximation because we cut it off at 2 decimals. But what I'm trying to show you is that if you calculate the square root of 12, you get this. And if you calculate 2 times the square root of 3, which is what we're saying the answer is, you get this. Now, here's what you do. If you go and take 3.46 times 3.46, and because remember, the point of a radical is to find something, when you multiply it by yourself, you're going to get the number under it. You're going to get 12. And that makes sense because you know that 3 times 3 is 9, and you know that 4 times 4, a little bit higher, is 16. It's somewhere almost in the middle. When you multiply that times itself, you're going to get 12, or a very close approximation to 12, because we have to cut the decimals off somewhere. All right. Now I want to show you one more thing, and this is actually also incredibly important. When we check these things, we can use decimals to kind of help us understand what we're doing, but you really need to get used to working with radicals. Okay. Let me go actually through the next problem and calculate that, and then we're going to go back to this and we're going to check this answer again without using any decimals. And it's important, but I think it's also important to just move on to the next problem before we get too bogged down over there. Let's take the square root of 8. All right. You can draw a factor tree for the square root of 8. And what is the square root of 8? Well, what is 8? 2 times what, right? You can say 2 times 4 is 8. And of course, this is prime, but the 4 can be written as 2 times 2. Now, everything in the bottom of the tree is a prime number. So now we look for pairs. We have a pair here, but we have an orphaned, a partner here that has no partner to it. There's no other part of the tree that can be paired up with this. So what actually happens is we say that the square root of 8 is equal to, the 2 here comes out because we found a pair, but this 2 stays under the radical, 2 times the square root of 2. This is actually the answer to this question, 2 times the square root of 2. Okay, now again, to check it, if you go to a calculator and find the square root of 8, what you're going to find is 2.83. Now I'm going to put a little approximate squiggly on there because it's not really 2.83, it's 2.83 and then infinite non-repeating decimals after it. All right, and then if you calculate this, the answer, 2 times the square root of 2, right? It's going to be 2 multiplied. When you put square root of 2 in a calculator, you're going to get 1.41 with a million infinite decimals after it. When you multiply these together, you're going to get 2.83. So what you calculate as the answer is exactly the same thing as what we found to be the answer. Of course, there could be minor differences in the last place of the decimal depending on where you cut it, but they are exactly equal to each other if you could carry all the decimals out. All right. And just to bring it all home, just like the square root of 36 is 6 because 6 times 6 is 36, if you take 2.83 and all the decimals after it and put it in a calculator and multiply it times itself, so 2.83 times 2.83, you're going to get very, very close to 8. It makes sense, right? Because 2 times 2 is 4, but this is closer to 3. 3 times 3 is 9. So grab a calculator, 2.83 times 2.83, you're going to get very close to 8. It'll be like 7.99 or 8.01. And if you carry more decimals, it'll get closer and closer to the truth. Now, we have more problems to solve. I don't want to lose you. So here in the beginning, I want to show you how to check these answers without using decimals. And this skill is very important because when we get to algebra, we're going to be working with radicals like they're candy. They're just going to be everywhere. And you need to be comfortable with how to deal with radicals. So let's go back to problem number 1. And we said that the square root of 12 was equal to 2 times the square root of 3. But the square root of 3 is not a perfect square. It's an irrational number. We approximate it as 1.73, infinite decimals after, but it's really exactly written as the square root of 3. So we take that square root of 3, we multiply it by 2. That is exactly what the square root of 12 is equal to. But if we get this as an answer, we just said 3.46 times 3.46 should be very close to 12. But this right here is the exact answer. So we should be able to take this, 2 times the square root of 3, and multiply it times itself. And when we multiply it times itself, we should get exactly 12. So multiplying something times itself is squaring it, right? So we're literally doing the same thing as getting an answer, 6 squared, 6 times 6 is 36. We check the answer. We get the answer, we're going to square this and see what happens. Now remember, from exponents, when you have things inside of a parentheses and an exponent on the outside, this exponent gets distributed into everything on the inside. You have 2 things multiplied together, this exponent applies to each one. So this exponent of 2 gets applied to the 2, and then we have the square root of 3. I'm going to wrap it in parentheses to make it clear, and then we have to square that as well. The exponent gets applied to every little thing inside. All right? Now, 2 squared is 4, and then we have the square root of 3 squared. But remember, in the last lesson, we said that the square root and the squaring operation, they're opposites of each other, right? Just like if you take, 10 squared and to take the square root of it like this, then what you're going to have is 100 on the inside, and take the square root of 100, you're going to get 10. You see, the square and the square root can be said to cancel because they're opposites of each other. They undo each other, and you just get back what you started with. And the same thing is going to be happening here. If you start with 100 here and take the square root of it and then square it, then on the inside, you're going to get 10 squared, and then you're going to get 100. So the same thing, you get the same number back. When you start with something and then do a square root and then a square, they cancel each other, leaving only the 100 behind, or whatever's underneath behind. If you do the opposite, square it and then square root it, the squaring and the square rooting, they annihilate each other, and you get back exactly what you had underneath in both cases. But here, notice that we have the square root of 3, and then we're turning around and squaring it. So this square root cancels with the square operation because those are actually called inverses. It's just like when you add 5. If I add 5 to something and then do the opposite, subtract 5, then I really have not changed anything. If I multiply by 10 and then turn around, divide by 10, doing the opposite, then I've not changed anything because those are opposite operations. Here I've square rooted this thing, but then I turn around and square it. Those are opposite things. So what happens is you end up with, since they cancel like this, 4 times 3. And what is 4 times 3? 12. And that is the check, because we said whatever answer we get, when we square it, should give us exactly what is underneath, and it does give us exactly what is underneath. So from here on out, I'm not going to check any of these problems with decimals, but I want you to know that if you take answers to any of these questions and dump them in a calculator, like 2 times the square root of 3 and you get a decimal, this number, when you multiply it by itself, should give you what's under there. When you dump this in a calculator, this number, whatever it is, multiply it times itself, you should get what's under here, but I'm not going to check it that way because we don't like decimals in math, because these decimals are approximate anyway. They're truncated. That's why we don't like to write the decimals down, because the actual number is not 2.83. It goes on forever. So this is the exact answer. Let's check this one. Okay. What we're saying is that if we take 2 times the square root of 2 and we turn around and square it, multiply it by itself, we should get this. the exponent goes in and applies to the 2. And the exponent also goes and applies to the radical. So I'll wrap that in parentheses, right? And so what's going to happen is this square is going to cancel with the square root that is there. You're going to be left with a 4 right there times 2, because this 2 is what's left behind, which is 8, which is exactly what is under here. So when you take this and you square it, you have to know, first of all, that the exponent distributes in, and you also have to know that anytime you have a square that operates on a square root, or backwards, a square root that operates on a square, they cancel each other, and you just have this behind. So 4 times 2 is 8, and we know the answer is correct. So as always, with these problems, the first 1 or 2 problems take forever. But now we can crank through, and you'll see how fast this process is, and we're going to check all of them to give you practice with that. You'll see how easy it is as we go. Let's take the square root of 18. So we'll do a factor tree. What times what is 18? You can pick whatever you want. I'm going to pick 9 times 2 is 18. The 9 I can write as 3 times 3 is 9. These are all prime numbers. We look for pairs of numbers because this is a square root, and we find a pair of 3's. All right? And so this 3 is going to come out as a single. It comes out of the radical because we found a pair, but this 2 has no partner. It stays under the radical, and we say that the answer is 3 times the square root of 2. If you go dump that into a calculator, you will get a decimal that when you multiply that decimal times itself, it'll give you 18. 18, because that's what's under there. Now let's check and see if this thing, 3 square root of 2, when you square it, multiply it by itself, let's see what happens. The 2 operates on the 3, making it 3 squared. The exponent also operates on the square root of 2 squared. I like to write that in parentheses there, just to make it clear. And then we see that this square cancels with the square root because they are basically undoing each other. And what you have left is 3 squared, which is 9, times the 2, which is left over after the canceling, and you get 18. And 18 is exactly what is under here, so we know that the answer is correct. 3 times the square root of 2 is the answer to this problem. And you see, even though I talked so much for the first couple of problems, this one went very, very fast. All right, let's take the square root of 20. What is the square root of 20? You can write whatever you like. I'm going to say that 4 times 5 is 20, but you could do 10 times 2, or you're going to get the same answer either way. 4, I can write it as 2 times 2. The 5 is prime. The 2's are prime, so I stop. And I'm looking for pairs, because this is a square root. I found a pair of 2's. So the single 2 comes out. This stays under the radical as square root of 5, and this is the final answer. That's it, 2 times the square root of 5. If you go in a calculator, take the square root of 5, multiply it by 2, you're going to get a decimal. That decimal, which will be infinite non-repeating, if you multiply it by itself, will give you 20. Now let's check and see if 2 times the square root of 5, if we square it, what happens? The 2 goes in, and the exponent applies to the 2. The exponent applies to the square root of 5. 2 times 2 is 4. The cancellation of the square and the square root happens, so 4 times 5 is indeed 20, and so that is exactly what is under there, so you know the answer is correct. You don't have to guess. All right, now I'll take a little pause here to tell you why we're spending so much time on this. We learned square roots with the easy problems first. You know, square root of 25 is 5, and I did the factor tree, even though it was very simple, to get you comfortable with it, so now hopefully it's not so scary, right? But we do that because later on we want to solve equations that are going to involve square roots and squares. And we have to know how to eliminate a square from an equation. For instance, if the variable you're trying to solve is squared, maybe it's a common one would be v squared, velocity squared. When you throw a baseball, a lot of times velocity ends up being squared. But if you want to solve for it, you got to get rid of the square. So you have to undo it with the square root. And vice versa. You can undo a square with a square root. You can undo a square root by a square. And so we're going to be working with variables very soon, x's and y's, that have square roots. And so we have to get used to this process with numbers, because when we do it with variables, it'll be much, much easier. Let's take the square root of 50. What is the square root of 50? I'm going to work on 10 times 5. You can pick whatever you want. It's not going to matter. The 10 I'm going to work on, or write it down as 2 times 5. And I'm looking for pairs of numbers. I see that I have a pair of 5s, and the 2 is left over. Now the single 5 comes out. This single 2, which has no partner, stays under the radical. 5 times the square root of 2, that's the full answer. Now let's check this guy. 5 times the square root of 2. We're going to square the whole thing. So you're going to get the 5 squared, and you put that exponent on the 5. You're going to have the square root of 2 squared. The exponent applies to both terms. And then what you're going to have is a cancellation between the squaring and the square root. 5 times 5 is 25 times 2, because this is what's left behind, 50. And that's what we were trying to find. That's what's under there. We square the answer. We get back what we're looking for. All right. I think we can do one more here. What about the square root of 27? Now, what I think of is 9 times 3 is 27, and the 9 I think of as 3 times 3. Now, I have prime numbers down at the bottom, so I stop and I look for pairs. I have a pair of 3's. So this 3 single comes out from the pair outside the radical. This one stays under. It has no partner. 3 times the square root of 3 is the correct and final answer. Let's check. If we have 3 times the square root of 3, the answer that we got, and we square it, multiply it by itself, then the exponent applies to the 3. The exponent applies to the radical, so we just square both little terms there. The cancellation on the square, I'm sorry, I put cubes here. My apologies. This is going to be a square and a square, so we're squaring everything. The square is going to cancel with the square root. Here we're going to have 3 squared. 3 times 3 is 9. This is what is left behind after this cancellation. And what is that? Look at that, 27, which is exactly what is under the radical. All right, now, so far, for every one of these problems, we've done square roots. Remember, square roots, you build your factor tree, you look for pairs. You look for copies because it's a square root. If you have a cube root, you do the same thing, but you look for triplets down there in the factor tree. If in the future you are working on a 4th root or 5th root or a 6th root, you can make up any root you want. A 4th root, for example, you build your factor tree and you look for copies, 4 copies, and you circle the 4 copies as a single which comes out. So the process continues for any kind of radical that you're trying to find. So let's go and take a look at the cube root of 16. The cube root of 16. Now, you can think of anything you want. I think of 4 times 4 being 16, but I'm looking for triplets of numbers, and that's not a triplet, that's only a pair. So I have no choice but to continue down 2 times 2. I still don't have any triplets, so I'm going to continue down and make this 2 times 2. And now I've broken the thing down into only prime numbers down here. And so I look for triplets, not pairs, triplets, because I'm not looking at the square root of 16. I'm looking at the cube root of 16. So there's 3 2's here. They come out as a single, but this 2 stays under the radical, but this radical is not a square root, it's a cube root. So this 2 stays under the cube root. So the 2 comes out because we found a triplet, and it's multiplied by, there's an invisible multiplication here, times the cube root of 2. And so that's the final answer. If you go to a calculator and you ask it what the cube root of 2 is, it'll give you a decimal. You multiply that by 2, you'll get another decimal. That will be the decimal answer of this cube root. Now remember, with a cube root, you check it by taking the answer and multiplying it times itself. You have 3 copies, you multiply it times itself. So what we have to do to check this thing is we have to take 2 times the cube root of 2, and we have to cube it. Because remember, for square roots, we just multiply it times itself to check it. For cube roots, the whole point of it is you got to find something that multiplies by itself, where there's 3 copies of it. So here we're going to cube it. Now this is an exponent like any other exponent, so it comes in here and it operates on the 2. It makes it 2 cubed. And then it goes and it operates on this cube root. So the cube root of 2 is here, but it's cubed as well. So we operate this exponent on both of them. What do you think is going to happen? The cube root cancels with the cube. This is not an exponent of 3. This is just telling you it's a cube root. It cancels with the cube. Just like a square root annihilates and cancels a squaring operation, a cube root or a cube annihilates or cancels a cube. So cube and cube root are opposites. Square and square root are opposites as well. So what do we have left? We have, this is 2 times 2 times 2. That's what 2 cubed is. 2 times 2 times 2. This is 8. And then this 2 is what is left behind after the cancellation. It is 16, and that is what is under here. So we know that this is the correct answer. 2 times the cube root of 2. All right, here's our last problem. Cube root of 128. Now, 128. What times what is 128? I happen to know that 2 times 64 is 128. You might not. That's okay. And I also know that 64 is 4 times 16. You could go a different direction with this, like 2 times 32, but I know that 4 times 16 is also the case. This 16, I can write it as 4 times 4. Now, if I wanted to, I could continue down with these 4s, and I can break them all into 2 times 2. You're going to get the same answer. But anytime you see a triplet, because you're looking for triplets here, you can stop, and you can circle that as a triplet. If you were to break it down into even more 2s, in fact, I'll do it just to show you in a second. Instead of just talking about it, I'll do it. What we have here is we see the 4, since we found a triplet, comes out. The 2 stays under the radical. So it's the cube root of 2. So it's 4 times the cube root of 2. All right, let's do it again real quick. 128, we're taking the cube root of that. We said 2 times 64. We said 4 times 16. We said 4 times 4. All right, now let's say you didn't see the triplet here. Okay, so this is 2 times 2. This is 2 times 2. And this one here is 2 times 2. You're looking for triplets. So here is a triplet. And here is another triplet, but this one has no partner. It's also in the bottom of the tree. So what do you get from this? This single 2 comes out, multiplied by this as a single 2 comes out, multiplied by this one, which stays under the radical. And 2 times 2 is 4 times the cube root of 2. 4 times cube root of 2 is exactly the same answer. All right, last thing, let's check this guy. 4 times the cube root of 2. We need to cube it and see what it equals. This exponent of 3 gets operated on the 4, and then it's operated on the cube root of 2. And what happens is this exponent of 3 cancels with the cube root, and so what you're left with is 4 cubed. That's 4 times 4 times 4, right? So 4 times 4 times 4. This is 16 times 4, which is 64. So 4 cubed is 64. So 16 times 4, 16 times, if you're not sure, let's just go. 16 times 4, 6 times 4, 24, and then 4 and 2, 6. So you have 64 here, and then what's left over here after the cancellation is a 2, and that's 128, which is exactly what is under here. So I know it may not seem so exciting, but this is actually a really important lesson because you would be stunned how many students get all the way to Algebra 2 or even into calculus, and they don't really know how to handle radicals. They never really were taught that a square root is the opposite of a square and that they can cancel each other. Then they were never really taught how to check your answer with, when you get an answer like this, how to check it and how that logic plays out, as we've done here over and over again. They were never taught. It's not their fault. It's just they were never taught that. And none of us are born with this stuff. But I'm trying to teach you that if you have a simple problem like the square root of 100, factor tree gives you the answer. Very simple, pair of 10s. But if you have square root of 105 or square root of 120, the problem is different, but you still attack it the same way. Build your factor tree. Any pairs you find, you come out with those, but whatever is left over just has to stay under that radical. And then the process is not mystical because it's the same process. You're not learning anything new. You're just continuing to apply what we know. I want you to practice every one of these, and I also want you to check every one of these. When you're confident you know what you're doing, follow me on to part 2. We'll continue building your skills with simplifying radicals. Learn anything at mathandscience.com.